Hello everyone, welcome to part 2 of function operations. We looked at graphical sums and differences of functions in the previous lesson. Today, algebraic. And this one is likely to be a little bit quicker than the previous. Graphing takes time because you actually have to plot points and connect the dots and all that jazz. But we'll see this one, we can probably speed things along. Now, we'll see examples where we're dealing with polynomial addition, but for the sake of looking at restricted domains, going to see some of our other functions pop up. Main part of this is just to make sure we can extract what the common domain is in any sum or difference function. And yeah, also a lot. To kick things off, if you have a function like this, so h of x is f plus g, and we want to get the algebraic formula for h of x, all we're really going to do is sub in this for f, sub in this for g. And then if there are like terms, we can combine those like terms. So h of x, is this on thick mode? No, it's not. Oh, I'm just zoomed in. And you know what? Let's just really change it up here. Ah, beautiful. So h is f plus g. F of x is x squared plus 3x minus 6. And g of x is 4 minus x. I know with addition these brackets aren't the most necessary. I like them because they help me keep track of what's what, that I can see that this is separate from this. Where do those two things come from? They came from f and g. So that's why I would put them there. Certainly necessary for other operations, but there's that. From here, we've just got two polynomials. We can collect the like terms. There's nothing that x squared is like with, it's got no friends, it's very sad. And then 3x plus negative x gives us this. Negative 6 plus 4 gives us that. And that's our sum function. If we took the parabola of the graph of y equals x squared plus 3x minus 6 and we added it to the line y equals 4 minus x, we would get this parabola here. It'd be pretty great. But we're not graphing things, we're just playing with the old equations and expressions here. I mentioned earlier something about the restricted domains. We saw from a graphical perspective, we could only add or subtract the functions if both existed at that point. If you try to add something to something that doesn't even exist, like, how do you even do that? I can't even comprehend. Can't just say, hey, subtract this. Subtract it from what? Doesn't make sense. Oh, boggling. Anyways, if we check out this example, where we have to state its domain. Let's start with actually finding what that sum function is. H of x is f plus g. Okay, well, I guess that means that h of x is f of x plus g of x. How do you go, right? Oops. There we go. And if we combine like terms here, ta-da. What's the domain of this? If you want, you can take a look at what the domain of the other things are. The domain of f, well, that's all real numbers. We know for any polynomial function that domain is going to be all reals. Domain of, is that the other one though? Domain of G? This one's got a radical. We know square roots can cause restrictions. We know we can't take the square root of negative, so that radicand, x minus 3, must be greater than or equal to 0, which means, of course, for our purposes, x has to be greater than or equal to 3. It's what overlaps between these that is the domain of H. This one says, hey, we've got no restrictions, so this one doesn't really factor in what causes things to change. This one says that x has to be greater than or equal to 3. If it's not, then G doesn't exist, which means that H can't exist. Therefore, the domain of H is same. That still follows into this next example. We have f minus g. Note the sign. Be careful of it. It sneaks up on you. You can still go through that process of finding what the equation is for h. Minus. Ooh, I don't like that G. So here's what H actually looks like, but its domain. Well, let's look at the domain of each of these functions. F is a logarithmic function. We know that we cannot take the log of anything that's not positive. So x has to be positive. And then we have a radical function. 5 minus x has to be greater than or equal to 0. Therefore, just don't forget the sign does have to be that way in this case. It is a common place where people can get tripped up. Again, stating that this radicand, 5 minus x, has to be greater than or equal to 0 is what allows you to solve that by adding x to both sides. Shaboom. The monster is eating the 5. And it's got an underline, because monsters have underlines sometimes. In any case, again, it's what's common to those that gives us the domain of H. There is a little bit of overlap, but as long as our values are positive and they're at most 5, we've got ourselves a stew. So a domain of H, all x, such that they're more than 0, but at most 5. Also, I know I've been using set notation for all these. If you want to just go interval on that, if interval works, then go for it. World's your oyster. Crack it open. Do you know? Do you feel? Do you dig? Sure. There's 2 more examples. They are very slight twists, if you will. More than anything, just make sure that you're paying attention to what it is you're actually tasked with finding in any instance. Like in this case, we see h of x is f of x plus g of x. You might just say, all right, I'm going to add this and this. Done. But, psych, this is h of x. That's not g of x. We need to find g of x. So, do be careful there. There's a number of ways to set this up. You might want to say that if h of x is f of x plus g of x, well then, g of x must be h of x minus f of x. It's not the only way you could approach this, it's the way I'm going to approach this. And in this case, h of x is 3x squared minus 2x minus 7. And we're going to subtract f of x, which is x squared minus 5x minus 8. And we'll get something out of that. 3x squared minus x squared, 2x squared. Negative 2x, go away family, I'm busy. Negative 2x minus negative 5x is, I don't even know where I'm at. That, and negative 7, and some other thing does that. Huzzah! And last example is just provide possible equations for f of x and g of x, such that this is the combo of f and g. There are infinitely many options here. Literally infinitely many. You don't have to get extra fancy with this if you're asked it. The instruction is just provide possible equations. Like, just make sure it works. One thing you could do, one option, is to say that f of x is x cubed plus 2x squared. That covers this first part. And then g of x could just be 7. And when you add them together, that gives you the whole thing. If you want to see some other options, oh, I'm going to provide them, don't you worry. Here's one option. You could say that f of x is x cubed plus x squared, and then let g of x have the other x squared that's supposed to be in there, and the 7. Another option, you say, okay, if you insist, here is one option. You could say that f of x is, I don't know, 3x squared plus x plus 9. G of x could be, I guess we still need that x cubed. We got too many x squareds. We gotta get rid of that x, we gotta get rid of 2. And if we were to add those together, yeah, we'd get h of x being x cubed plus 2x squared plus 7. And if you want to be a little cutesy about this, here's a cheeky option. H of x is f of x plus g of x, you say? Okay. Look at this. I've let f of x just be the same thing as h of x. What do I add to that to make f of x equal, f plus g equal to h? Literally nothing. And if I add those two together, I'll get my result from up top. And that's what you know about algebraic sums and differences of functions. There is a whack ton of practice. Ka-chow! Practice it all. Enjoy it, love it, cherish it. Math is beautiful. And believe in yourselves, believe in the dream. Don't forget to contact me if you have any questions at all as you proceed through any of that. Peace, love, harmony. Goodbye.